Right. So yesterday we were in the middle of looking at angles that are not the quadrantal angles. So we started by looking at the 45, 45, 90, figured out the coordinate for it. Someone remind me, what was the coordinate for a 45-degree angle? Yep, Jackson.
Rad 2 over 2, rad 2 over 2.
Yep, so that's the coordinate for 45. So now we're going to look at the other two angles that are common, the 30 and the 60. Okay, and we're going to figure out the coordinate for those. So we've got our diagram. Okay, I just drew the same triangle that's in that circle off to the left, a little bit bigger. But the goal is to figure out the coordinate for 30 degrees. Okay, remember the coordinate is directly related to the length of the sides. How far to the right you have to go, that's going to be your x. And then how far up you go, that is your y. Now, what do we know about a 30, 60, 90 when we're talking about the sides? Just very, very generally. Anything you can tell me about the sides? Okay, very, very general.
None of the sides are equal.
Yeah, they're all different. Okay, since they're all different, we can't use Pythagorean theorem right away, because if we try to label these sides, we'd have to use two different letters because they're not the same. And if we try to solve this, well, even though we know the hypotenuse, you'd have x squared plus y squared equals 1. We can't solve that with two different letters. So we've got to figure out one of those other letters first, a different way, then we can use Pythagorean theorem. And my hint, which we had just started talking about, was to take this, go like that, and that's about where we stopped. Okay. So, any suggestions on what I can do with that? Yep.
If you take the second triangle and you mirror it,
Mirror it?
it would be mirrored left to right.
Okay.
And then you put the vertices, the 90-degree angles, up against each other, and it creates a triangle with two equal sides.
That does create a triangle with two equal sides. Yes, it does. Okay. So what would I do from there?
You could label that bottom length 2x for now, and then you are able to never mind.
Okay, so we did create a triangle. Not 100% sure how we could do it that way. Maybe there's a way, but anybody have another thought of what we could do kind of similar to that, but a little bit different? Yeah?
Like mirroring it so that it's like up and down.
Okay, so let's mirror it up and down. All right.
And then putting it like the longest, like not the hypotenuse side, but the top side, the triangle right now.
The long leg.
Yeah.
Okay.
And then that'll make it like the 60 degree, 60 degree, 60 degree.
Yeah, so what we want to do is put it like that. And now we've created another triangle just like we did a second ago, but I think that one is kind of important, what we just did. What kind of triangle did we just create there? Yeah?
Equilateral.
Right, we have an equilateral triangle. Jackson just said 60 and 60 and 60. All the angles are 60 degrees. If it's equilateral, what does that tell you about the sides? Yeah?
They're all the same.
They're all the same. So we know this side at the top is 1, this side at the bottom is 1. And what else do we know? Yeah?
All the other sides are 1.
Right, the right side is also 1. Right, that has to be 1 unit from there to there. Well, if we know that entire side is 1 unit, what can we do from there to figure out one of the sides in our original triangle? Yeah?
Divided by 2.
Right, because we know these two sides are congruent because they're just reflections of each other. So if you're going to add two things that are congruent and it has to total 1, the only option is for each one of them to be 1/2. Now we just figured out one of the other sides in the triangle. We can use Pythagorean theorem to finish it and get the last side. But we don't need this bottom triangle. We don't need any of that anymore. Just need this. All right, so let's use Pythagorean theorem and find the bottom side. What could we call the bottom side for now? Yep.
X.
Yeah, let's call it x. And can somebody set up my Pythagorean theorem for me using the three labels that we have on that triangle? Yeah.
X squared plus 1/4 equals 1 squared.
Okay, so we got x squared plus 1/4 equals 1. Okay, so bring the 1/4 over. So we get x squared equals 3/4. And how are we going to get x by itself? Yep.
The square root of the sides.
Yep. And how do we take the square root of that fraction? No, you don't flip a fraction to take the square root of it. But we do have to take a square root. Yeah.
I do the square root of the top and bottom.
Right. Take the square root of the top and the bottom. When you square root the top, 3 is a number we can't take the square root of. It's not a perfect square. So we're just going to leave it as the square root of 3. But we can square root the bottom, and we get 2. So now we know the length of the bottom side of the triangle is root 3 over 2. That should be enough information to give us the coordinate for 30 degrees. Can anyone give me the coordinate now for 30 degrees? Yes, Raj? 3 over 2, yep, and 1/2. Exactly. So to get to the point where the terminal side, if you made this into an angle, just like this, to get to the point where the terminal side of your angle hits the edge of the circle, you go right root 3 over 2, and you go up 1/2. Now, just to put those two numbers kind of in perspective, which one of them is bigger? Root 3 over 2 or 1/2? Well, Nick, what do you think? Yeah, root 3 over 2 is bigger. First, we can tell in the diagram it's the longer side because it's across from a bigger angle. So the 30 has to be the smaller side. Or the side across from the 30 has to be the smaller side because it's across from the smaller angle. So root 3 over 2 is about 0.866. 1/2 is 0.5. So the root 3 over 2 is definitely bigger. So we got the coordinate for the 30. Now we need the coordinate for the 60. Right, so when we do the 60, we're going to have a triangle like that. How are we going to get the coordinate for the 60? Yeah?
You just flip the coordinates because it's the same triangle.
Yeah, it's the same triangle, right? We're dealing with a 30, 60, 90 again. The difference is now the 30 is up here, and the 60 is that piece down there. So it's the same triangle. We just have to remember that the side across from the 30, that's always the short side, which is the 1/2. And the side across from the 60, that's this side, that's the long side. That's originally the side that was horizontal. Now it's vertical. So it's root 3 over 2. So that's the coordinate for 60. And now let me just put the, let's put the 45 on there too. So 45 would be right there. Draw that. Draw that. And that's all 3 triangles that you can make in the first quadrant. And that's root 2 over 2. Root 2 over 2. So those are the coordinates that you need to remember in quadrant 1. Now, I'm not going to do this for every angle, but let's do it. Let's try it for the 45. Let's say I reflect that red dot over the y-axis. What angle would this represent over here? Yeah?
135.
That's 135. And if we make a triangle out of it, we should be able to figure out the coordinate for 135. Does 135 degrees have something to do with one of the 30 and 60 triangles? Or does it have something to do with the 45 triangle? Which one?
45 triangle.
Right, it has to do with the 45 triangle. Because if you think of this as being 90, and you're trying to get to 135, ask yourself, what do you have to add to 90 to get to 135? Do you add a multiple of 30? Or do you add a 45 to it? And the answer is you add 45 to get from here to here. So this angle is 45. That's between 90 and 135. And then this angle also has to be 45 because the entire quadrant is a 90. So it's the 45, 45, 90 triangle reflected into quadrant 2. So, anyone think they could tell me what the coordinate would be for 135? Yeah?
Just be negative root 2 over 2, and then just add 2 root 2 over 2.
And then root 2 over 2. That's the coordinate for 135. So there's 12 different points that we can figure out now, 3 in each quadrant, that are multiples of 30 and 45. You can do the 45, the 135, this is 225, and that would be your 315. Okay, I'm not going to start drawing every triangle because then it starts to get really messy. And then the 30 in every quadrant, you've got the 30. Over here, what angle would that be? Yep.
60.
Well, it's going to be bigger than 135 because that's 180.
150.
Yep, that's your 150. And then we could take that same point and reflect it down here. What angle would that be? Yep,
210.
that's your 210. And we could take this same point and then reflect it down there. What angle would this one be? Yep.
-3.
Well, let's just do it as a positive.
330.
330. Yep. Okay, so that's that triangle reflected in every quadrant. And then we can also reflect the 60 in every quadrant. So that point would end up here. What angle would that be? Yep. So that's your 120. We can take that same point and then reflect it down here and then over there. What angle would this be? Yep. So 240. I'm going to move the 225 so it's in a better spot. 225, 240, and the last one right there. Yep.
300.
Yeah, 300. Okay. So those are all, let's get rid of that so it's not right next to it. Those are all the different angles that you can do on the circle. And every one of the coordinates you can figure out because they are just reflections of what's in quadrant 1. Any questions on that? Okay, so now we'll go through some of those different points. Don't forget, there are 4 other points that we did. Those are the quadrantal angles. 0, 90, 180, and 270. Okay, so now that gives you a total of 16 different points. Okay. 70 and 0. All right, so let's try to find the 6 trig functions of 45 degrees. All right, what's the first thing we have to do to figure out the 6 trig functions of 45 degrees? Yeah.
Find the group of 45 degrees.
Yep. So we got to find the coordinate. Okay. If you have to, in your head, you can try to think of what the sketch would look like. Something like that. So we know we're dealing with both positive numbers because it's quadrant 1. And can you give me what they both are for 45?
Brad, 2 over 2. Any other one as well?
And the other one as well, yep. Okay. So let's go through all 6 of them. I know we just did it in the homework, but we'll do it one more time. What's the sine of 45 degrees? Yep.
Brad, 2 over 2.
Okay, so 2 over 2. Cosine of 45 degrees? Yep.
Brad, 2 over 2.
It's also root 2 over 2. Only reason they're the same is because the x and the y are the same. Generally, they're not always the same, so you don't want to mix them up. Okay. And how about the tangent? Yep. 1. Okay. What about the cosecant of 45? Yeah.
Brad, 2.
Yeah, we just want to memorize. We don't want to have to deal with flipping it, getting the root in the bottom, multiplying by root 2, canceling the 2's, and reducing. We just want to remember when you flip root 2 over 2, it's root 2. So that's also root 2. And the cotangent of 45? Yeah, 1. Good. So that's how we want to be getting pretty quick at it. Good. Okay, any questions on those 6? Let's try the 6 trig functions of 30. So 30s and 60s, you got to be careful because it does involve the 1/2 and the root 3 over 2, but you have to get them in the right order. Okay, so what's the coordinate for 30 degrees? Yep.
3 over 2.
Yep. And if you forget it, okay, in your head, try to visualize where 30 degrees is. It's lower on the circle in quadrant 1. Okay, it's lower to the x-axis. That means when you draw your triangle, the green side is going to be the long side, and the purple one, that's the short side. The long side is always root 3 over 2. The short side is always your 1/2. Okay, and now let's go through all our trig functions. What's the sine of 30 degrees? Yep.
1/2.
1/2. And the cosine of 30 degrees? Yep.
Root 3 over 2.
3 over 2. Now, the tangent, if you're not sure, because it's the first time we've seen the tangent, it's y over x. So it's 1/2 divided by root 3 over 2. When you divide those, what's going to happen? Yeah?
The 2's cancel.
The 2's cancel, because you'd flip and multiply, and you'd be left with 1 over root 3, which we need to fix to be root 3 over 3. So that's the tangent of 30 degrees, root 3 over 3. Okay. How about the cosecant of 30 degrees? Yep.
2.
2. Okay. How about the secant of 30 degrees? Completely fixed, no root in the bottom. Yep.
2 root 3 over 3.
2 root 3 over 3. And how about the cotangent of 30 degrees?
Root 3.
Root 3. So you have two things you could flip. I would flip the 1 over root 3 because when you flip that, the root goes to the top and you're done. If you flip your final answer that you had for tangent, you're going to put the root back in the bottom and then you're going to fix the whole thing again. Okay. So those are your 6 trig functions for 30. Any questions on those? Okay, I think we got like one more where we do all 6 and then we're going to start just maybe finding some of the trig functions. Just sines and cosines and tangents. All right, so we got the 30s and 6 trig functions of pi over 3. What's the coordinate of pi over 3? Yep. 1/2. Yep, 1/2 root 3 over 2. Pi over 3 is 60 degrees. If you sketch a 60, that's going to be the version of the triangle that's standing taller, not laying down. 60's up here. That makes your short side the bottom, and it makes the height the tall side. So the 1/2 is on the x, and the root 3 over 2 is on the y. Okay, let's go through all our answers, and then I want to compare them to the ones we just got. What's the sine of pi over 3? Yep.
Root 3 over 2.
Root 3 over 2. What's the cosine of pi over 3? Yep.
1/2.
1/2. And what about the tangent of pi over 3? Marcel? Root 3. Yep. And now to get the other ones, we're just going to flip them. So this is going to be 2 root 3 over 3. This is going to be 2. And the last one is root 3 over 3. What do you notice if you compare all the answers that we got here to the answers we got on example 2? Yep.
They're the inverse of each other.
What do you mean? They're the inverse of each other.
Well, actually, no, it just applies to tan. Well, I was looking at tangent and cotangent, where the tan of 30 degrees is the inverse of the tan of pi over 3.
Can you explain it without, because inverse means something very special when we talk about trig. Can you explain that without using the word inverse?
I'm forgetting the correct term.
Okay. Vanessa?
The answers for sine and cosine are flipped, and then tangent and cotangent are also flipped. So sine's answers go to cosine, and cosine's answers go to sine,
Yeah.
and then the tangent and cotangent just flip sides.
So those two switched, which means those two switched, and those two switched. Those are the pairs of trig functions that flipped when we went from finding the trig functions of 30 to the trig functions of 60.
Oh, I thought I meant to say the reciprocal. So,
Well, the only ones that actually flipped that are reciprocals of each other are tangent and cotangent. Sine and cosine are not reciprocals. Sine and cosecant are reciprocals. But sine and cosecant did not switch places. That's not how the switching worked. The way the switching works here is these are what we call co-functions. A co-function is when you put the word co in front of the name and we get the other function. So sine has a co-function of cosine. Secant has a co-function of cosecant. And tangent has a co-function of cotangent. So for tangent and cotangent, there's they're special because they're not only co-functions of each other, they are also reciprocals of each other. Okay? But everything in those blue boxes, the pairs that you see, are what you call co-functions. And we'll study a little more about co-functions some other time. All right. So we've done everything we can do in quadrant 1. We did the 30, the 60, and the 45, and we did all 6 trig functions. That's 18 answers, and we did them all. Now we're going to be a little more selective and do some of the trig functions. We're going to do 135. Okay, so what's the first thing that we need to figure out to do those 3 trig functions of 135? Yep.
Find the coordinates.
Right, we've got to find the coordinate. So what I like to do first is think of, okay, 135 is in what quadrant? Yep,
The second.
it's in the second quadrant. So we're looking for a negative x and a positive y. And now we have to think 135. Does that have to do with the root 3 over 2 and 1/2 numbers? Or does it have to do with the root 2 over 2, root 2 over 2? Yep.
Root 2 over 2.
Right, it's the root 2 over 2 because 135 is halfway between 90 and 180. That makes it a 45-degree angle triangle. Okay? So we're looking for a coordinate for a 45-degree angle, but it has to be in quadrant 2. So what would be your coordinate for 135? Yep.
Negative root 2 over 2, and then right 2 over 2.
Yeah. And this time we're just doing sine, cosine, and tangent. You still have to know all of them, but we've done a lot of all of them, so I'm trying to do some different ones now. Okay, what's the sine of 135 degrees? Yep.
Root 2 over 2.
Yep, root 2 over 2. What's the cosine of 135 degrees?
Negative root 2 over 2.
Negative root 2 over 2. And what about the tangent of 135 degrees? Negative 1, because we're dividing the y by the x, and they're opposites. Okay. Any question on sine, cosine, and tangent? Okay. Let's try this one. The 6 trig functions of 7 pi over 6. What's pi over 6? Yeah. That's 30 degrees, right? Pi is 180. So that's 180 divided by 6. So it's 30 times 7. It's 30 times 7. That's
210.
210. So now we have to figure out the coordinate for 210. Okay, first of all, what quadrant is 210 in? Yeah. Yeah, it's going to be somewhere, we're looking for somewhere in this quadrant. So we know that the x is negative and the y is negative. And now 210. We got to figure out, does 210 involve the 1/2 root 3 over 2? Or does it involve the root 2 over 2s? Which pair of numbers?
8 involves 1/2 root 3 over 2.
Right, that's a multiple of 30. Okay, we know it's 30 times 7. That's how we figured it out. So because it's a multiple of 30, it's going to involve the 1/2 and root 3 over 2. They're both negative, but we got to get them in the right order. So when you draw your circle, think of where 210 would be. 210 is just a little bit past the horizontal. That's the diagram you should think of in your head. So now you can see which side is the long side and which side is the short side. So what's going to be my coordinate for 210? Yeah. Negative root 3 over 2, negative 1/2, Now we can do our trig functions. Okay. Greg, what's the sign going to be?
The sign is going to be -1/2.
Yep. -1/2. My cosine, Ethan, what's that going to be? -√3/2. And what am I going to get for my tangent? Yep. √3/3. Yep. Because when you divide these, the negatives are going to cancel, the 2's are going to cancel, and you'd be left with 1 divided by √3. Well, you just have to fix that so the √3 is not in the bottom, and it's √3/3. Okay. So, any questions on trig functions of 210? All right. So we can work with any angle on that circle that's a multiple of 30 and 45. And I gave you a chart that goes through all the different angles. So is there any question on how you would find the coordinates of any of the 16 angles that are on the board? Okay, so those are the ones you have to know for the test tomorrow. Specifically, as long as you know those 3, you pretty much can figure out anything else you need to, just by reflecting it. Okay, so unit circle trig works great when you have angles that are multiples of 30 and 45. It also does work for multiples of 15. Okay, we didn't do the 15 and the 75. You can, but we don't have enough information yet about trig to do that. So we'll come back to the 15s and 75s in probably a couple months. All right, so when you don't have a multiple of 30 or 45, we are going to use the calculator, which means the answers are going to be rounded, generally 2 decimal places, unless the directions say otherwise. When you're using the calculator, it's very important you put it in the right mode. Okay? If you are dealing with a problem that is degrees, you need to make sure it's in degrees. If you've got a problem that is, I don't know if I think I have one in radians somewhere. Yep, that 6b is going to be in radians. We need to switch over to radians. There's nothing to remind you whether you switched it or not, because if I do cosine 42, it'll give me the answer, and that's in degrees. If I put my calculator in radians, it will also do cosine 42. But they're totally different answers, and it's not like I get an error if I'm in the wrong mode. Calculator just thinks you want 42 radians in the bottom one, and 42 degrees in the top one. So just make sure you're in the right mode. So the first problem, we know it's in degrees because we've got the label on our angle, the little circle. And we pretty much just type them in. So we're going to do sine 42, cosine 42, tangent 42. That's how you do the first 3. And you know what? Rather than write them, I'm just going to put that right there. Any questions on those? All right. Now the next 3. I don't have any buttons on the calculator that say cosecant, secant, or cotangent. So we need to find those the exact way we've been finding them all along. How do you think you're going to find the cosecant? Yeah?
Putting the sine, cosine, or tangent, or cotangent, or tangent as the denominator.
Yeah, we're gonna flip them all. So if you want to know the cosecant, you're going to do, let me clear it so I have a nice screen, 1 over the sine. We took the sine and we flipped it. If you want the secant, you're going to do 1 over the cosine. And if you want the cotangent, you're going to do 1 over the tangent. Now, why did I type it in like that rather than doing 1 divided by like 0.74? Yeah?
Because the 0.74 is the exact answer of the cosine of
Yeah.
it, so you have to do a whole number.
Yeah. So I did that so I'd have more accuracy. Right? If I round it to 0.74, well then I've lost the 31, 44, 82, 55 after it. So when you need to find the reciprocal of a trig function, use 1 over and then write the trig function just like I did there. So there's your next 3. Okay, so there's all 6. Sine, cosine, tangent. This is the, cosecant, secant, and cotangent. And if we round it to 2 decimal places, it would be 0.67, 0.74, 0.90, 1.49, 1.35, 1.11. Okay. Let's look at this one. Kind of already told you what's different here, but what's different about this question? I mean, besides they're only asking for 2 things instead of 6 things. Later? It's in radians. Okay, you know it's in radians because anytime that you put a number there, this number always represents an angle. An argument to a trig function is always an angle. So that's 10, no label, radians. Okay, so the easiest way to do it is change your calculator into radians and then do the sine of 10 and the cosine of 10. There's your 2 answers. Now, and if you round to 2 decimal places, the sine is 0.17, the cosine is 0.98. Did I change to, I thought I changed to radians. I'm sorry. Let's type them in again. Sine of 10. Maybe I did press it, because sometimes I press it and it doesn't, it's like maybe I didn't press it hard enough or something. Cosine of 10. All right. That looks better. So negative 0.54 and negative 0.84. Now, how could you do this problem if you didn't have a mode to change to radians? Let's say your calculator is stuck in degrees. What could you do? Yeah.
You could switch it to degrees.
Switch what?
The radians.
Like the mode on the calculator?
No, like you could multiply it with the radians.
Yeah, what would you multiply 10 by to change it to degrees?
Times 180 with 180.
You multiply it by the 180, yep, and then divide by
The radian.
pi. Yep, so multiply by 180 over pi. If you leave your calculator in degrees and you do that, you should get exactly the same answer. 10 times 180 divided by pi. Order of operations is fine. The calculator will figure all that out. But I get exactly the same answer, negative 0.544. So you can leave it in the same mode if you want to convert it manually. I generally switch the mode. Okay, the only danger with switching the mode is you might have to go back and forth several times depending on the question. Okay. Any question on that? Okay, so we've looked at 2 out of the 3 things in the section. We did the 30s, 45s, and 60s with the multiples. We did using the calculator to work with angles that are not multiples of 30 and 45. And the last thing we're going to look at is some special properties and connections between different trig functions. We already talked about these 3 things. what is the connection between sine? I'm looking for the proper word. Between sine and cosecant, cosine and secant, and tangent and cotangent. They are, yep. So if you put the word co in front of this, what do you get? Do you get this? Yeah.
No, you get cosine.
Yeah, so sine and cosine would be cofunctions. But this is another relationship we talked about. Yep.
They're both reciprocals.
They are reciprocals. Okay? You flip the one on the left to get the one on the right. And that's true all of the time. It's not just true like if you want to find the sine of 3 degrees, like it only works for 3 degrees. No, it works for any degree. 3 degrees, 12 degrees. Anytime you flip the sine, you get the cosecant. Well, if it's true all of the time, that's called an identity. So what I'm writing on the board right now are what are called the reciprocal identities. There's really only 3. It looks like I've written 6. But the ones in the same row are actually repeats of each other. It's kind of like if I wrote a formula like this, and then I wrote it like this. Well, that's the same formula. It's just, you just move something to a different spot. And that's exactly what's happening here and here. Those are exactly the same formula. Okay, I think even a better example would be like distance divided by rate equals time. All you've really done in those 2 formulas is you switched what was on the bottom and what was on the other side. And that you can always do that in a fraction. If you switch what's the denominator with what's on the other side, and it's just set up where you have a single fraction and a single term, you can always switch these 2 things and get another fraction that's equivalent. Okay. And that's what I did in each of the 3. Okay. So if you flip the sine, you get the cosecant. If you flip cosine, you get secant. And if you flip tangent, you get cotangent. And then if you flip it back, it goes back. If you flip the cotangent, you go back to tangent. If you flip secant, you go back to cosine. And if you flip the cosecant, it goes back to the sine. Those are what we call the reciprocal identities. Okay. Any questions on those? All right, so that's one property I want to look at. The next property. This is going to be the first time we've seen the graph, but I want to show you a picture of what sine looks like. That's what sine looks like. It's not linear, it's a wave. And what does it look like the domain is for sine? Yeah?
All real numbers.
All real numbers. It's a wave that goes left and right forever. How about the range? Does it look like the range is?
Looks like it goes from 1 to -1.
It does. It goes from 1 to -1, and cosine is exactly the same. But how would you describe the transformation between sine and cosine? A reflection, a shift, a stretch? What do you think? Yeah?
Shift.
Yeah, it's a horizontal shift. Okay. And it's actually a shift of 90 degrees. Okay. So if you took this blue one and you did a horizontal shift to the left by 90 degrees, it would look exactly the same as the red one. So when we're talking about sine and cosine, the domain is all real numbers, and the range is -1 to 1. None of the other trig functions have properties like that. Sine and cosine are very different than the other ones. Sine and cosine are also continuous. You never have to lift your pencil when you draw it from beginning to end. Every other trig function is discontinuous. And what would you have in a graph that makes something discontinuous? Besides a hole, what else can make something discontinuous? Yeah?
An asymptote.
What kind of asymptote? Vertical, yeah. Every other trig function, I'm not going to draw all of them, but I'll draw a tangent. Every other trig function besides sine and cosine has vertical asymptotes. And the vertical asymptotes for tangent, they occur very regularly. Eventually we'll learn how often they occur. But they break the black graph into separate pieces. If I drew cotangent, secant, and cosecant, they would look a little different, but you would still see them broken into pieces. Okay. Sine and cosine are the only connected graphs. That's why the domain is all real numbers. All right, so let's look at one more thing. Let's take the sine of 10 degrees. And I get that. Can somebody give me something else I could take the sine of, and it would come out exactly the same as 10 degrees? Yep.
370.
370. Yep. Or written a little clearer, 10 plus 360. How about something else I could take the sine of that would come out the same as those? Yeah.
Negative 350.
So we could do the sine of 10. Let's think of it as minus 360. So in other words, you can keep adding or subtracting 360 as many times as you want. Right? If I added it 2 times, that would be the sine of 720 plus 10. 730. They're all coming out the same. This is called the periodic property of sine and cosine. Periodic means that you will continue to get the same answers over and over. That's what periodic means. And that's exactly what these graphs are. These are called periodic graphs because they have the same look over and over. Okay? Once you know what part of the graph looks like, you know what the entire thing looks like because it just keeps repeating itself. So if you take sine and you add or subtract, and n could be a negative number because integers can be negative, you can add or subtract any amounts of 360 and you will always get the same answers when you do sine and cosine. And if you want to do it in radians, you could add and subtract multiples of 2 pi. Okay, so if I take something like the sine of 1.5 radians, or the sine of 1.5 radians plus 2 pi. Same thing. I can add or subtract 2 pi as many times as I want, and it will never change the answer to a sine or a cosine problem. That's what this is saying. Any questions on that? Okay, and the last property. So I have already given you some of the fundamental trig identities, the reciprocal identities. Those are what we call fundamental. They're basic. Okay, I'm going to give you 2 more to add to the reciprocal identities. They're not reciprocal, they're fundamental identities. They're a little different, but I want to add them to the 6 that you already wrote down. Let's see, what did I write? Okay, go on the next page. So remember, these are formulas that are true all of the time. It's not like they only work for even angles or odd angles. No, they work all of the time. That's why they're called identities. Okay, so you've already written down all the reciprocal ones. Okay, here's the two that I'm going to add. We wrote this earlier. These are the definitions of the trig functions on the unit circle. Can somebody tell me a different way that I could write tangent based on what I have right there? Yep. Yeah, you can write tangent as sine over cosine. So what that means is if you wanted to figure out, let's say, the tangent of 4.3 radians, and for some reason you didn't have a tangent button, but on my calculators you always will. You could take the sine of 4.3 and divide by the cosine of 4.3. Dividing the sine by the cosine gives you the exact same thing as the tangent. You can also see that graphically. If I take sine and divide by cosine, if I graph that, and then I graph, well, I got a second window. Okay, that's sine divided by cosine. And now watch what happens when we graph tangent. It's hard to tell, but it is tracing over the blue one in black. They're the same thing. So that is an identity. Sine divided by cosine will always give you tangent. So what's the advantage of that? Well, if you've got a problem and it has a lot of trig in it, and you see sine divided by cosine somewhere, that's complicated, right? It's a fraction, and it's got two different trig functions. Well, anywhere that we ever see a sine over a cosine in a problem, we can just change it to a tangent. That's simpler. It's a single trig function, and it's no longer a fraction. So the goal with these identities is to try to simplify things that look complex. What about cotangent? How do you think I can write that based kind of the same idea?
It's cosine divided by sine.
Yep, it's cosine divided by sine. Okay, there's one more group of identities. I'm not going to add them today, though. They're called the Pythagorean identities. You don't need to know those for tomorrow. Okay, just those. So when we're working with identities, we're getting away from numbers. Okay, we're not actually thinking about plugging in a specific value for theta and trying to figure something out. We're looking at something that just has trig in it and trying to make that look simpler. Okay, that's the goal. Okay, so I don't want to worry about this top piece right now. But the reciprocal identities that I gave you, they do work for higher powers. So if you flip the sine, you get the cosecant. Well, if you flip sine squared, you get cosecant squared. And if it doesn't make sense, why? Think about what sine squared means. It means sine times sine. Sine, 1 over sine. That's sine squared if you multiply it together. 1 times 1 in the top, sine times sine in the bottom. Well, if you did each one of these individually, 1 over sine is cosecant. 1 over sine is cosecant. And whenever you multiply two things that are the same, you get that to the second power. So that's cosecant squared. Okay, any of these ones that are on the board on the left side, they all work with higher powers. What do you think sine squared divided by cosine squared would be? Yeah. Well, sine over cosine is just tangent. But sine squared over cosine squared would be something different. What?
Would it just be tangent squared?
Yeah, it would be tangent squared. Okay. If you ever get stuck, kind of break it down and think about, okay, so sine squared over cosine squared. That means sine times sine in the top, and it means cosine times cosine in the bottom. And now think of it as two different problems. Sine over cosine, that's tangent. Sine over cosine, that's tangent again. And tangent times tangent is tangent to the second power. This is how you write tangent to the second power. It's just kind of a convention. They put the 2 right in the middle. That's just how they do it. But yes, it does mean the same thing as this. You just usually never see it the way on the right, even though that's how you would normally think of raising something to the second. That's how you do it. Okay. So let's see if we can simplify this identity. Okay. I want to make it look simpler than it does right here. The trick that you generally want to try for now is to change everything to sines and cosines and then hope that something cancels out. So let's start with cosecant. How could we rewrite that just using sines and cosines? Yeah.
1 over sine.
That is 1 over sine. How could we rewrite tangent using sines and cosines? Yep.
Sine over cosine.
That would be sine over cosine. What's going to happen when we multiply those two things together? Yep.
The sines cancel out.
The signs cancel out. It's just like multiplying 1/3 times 3/5. Okay, those cancel out. What are you left with if those cancel out? Yeah. 1 over cosine. And what is the cosine flipped? Yeah.
Secant.
That's the secant. Perfect. That's the idea of simplifying a trig identity. You took something that had two different trig functions with multiplication, and you turned it into just a single, simpler trig function. All right, so let's try one more of those, and that'll be it. These are pretty quick. Identities can get very complicated, very complex. These are not. How can we rewrite secant? What? 1 over cosine. How would we rewrite cosine? We wouldn't. It already is cosine. What happens when you multiply those together? Yeah.
Cosine cancel out.
Cosine cancels out, and this time all the trig disappeared. That won't always happen, but it did here. What does that reduce to? Yeah, 1. And it should be because secant and cosecant are reciprocals. Anytime you multiply two things that are reciprocals, like 1/2 and 2 over 1, they always cancel each other out, and you get 1. Okay, so that's all for trig identities. That's all you need to know for now, is change them to sines and cosines using the fundamental identities, and then something will cancel out. They get harder, but not on this test. All right, so those are the questions for tonight. There's one question I added. I want you to try to simplify secant squared divided by tangent squared. And I guarantee with the formulas I gave you, you can do that. Okay, what I'll do is I'm going to leave that up while you guys are gone. I'll put the topics that are going to be on the test, and then I will upload that video in a little bit. So you can skip question 50.
Thanks, Jacob.